The title of my talk, Experimental Quantum Computing at IBM. It's a very generic title. But what I wanted to talk about is the type of devices that we have and we use at IBM, and focus on what type of controls that we use to implement quantum gates, and also the different methods that we use to characterize, and mainly to understand our quantum system. And that would help us improve our devices and move forward in terms of trying to use this as a good quantum computer. So, quantum computing technologies. There are many types of quantum computing technologies, and you could ask the question, what's your favorite qubit? And some might answer ions, photons, nanowires, solid-state defects, neutral atoms. But at IBM, we like superconducting circuits. So in this talk, I'm going to focus on this superconducting circuits. And a very brief outline, as I said, the main part of this talk is going to be understanding our quantum system and discuss different things. And I know the topic of this workshop is quantum application, near-term applications, or approximate quantum computing. So briefly, I will talk about what can we do with noisy quantum system, which is, I'm just going to talk briefly on our recent results on quantum chemistry. So from the very basic, the type of qubits that we have is a single junction transplant qubits. We have, it doesn't show much. So here we have our Josephson junction. It's a layer of aluminum, aluminum oxide, aluminum. And the Josephson junction is a nonlinear inductor, which is, for a transplant qubit, is shunted by a large capacitor. So rather than having a harmonic oscillator, you can make this anharmonic oscillator so that the lowest two energy level is separated from the higher levels. And we're going to use the lowest two energy level as our qubits. So here is our qubit, and what does it happen when you couple this to a resonator? A resonator is just a regular LC circuit. And here's the Hamiltonian of the interaction between the qubits and the resonator. And then the dispersive limit, where the qubit frequency is well detuned from the cavity frequency. The cavity frequency depends on the state of the qubit. So that is how we are going to read out the state of the qubit. Here's a sample of a 2-qubit device, 2 transplant qubits, coupled by a coupling cavity, which I'll call a bus. And each qubit has this readout cavity. And depending on the state of this qubit, when you put a tone, a microwave tone in this cavity, you sweep the frequency, you'll see a state-dependent resonance. So this is how we're going to probe the state of the qubit. And typically, we would have amplifier attached to the readout resonator, and we could do a high-fidelity readout. Here's a histogram of the ground state and the excited state of the qubit. And you could see that the states are very well separated. And you could get a readout fidelity from that. So in terms of readout, so currently we have high fidelity readout using some type of quantum limited amplifier, such as JPCs, TUPAs. But right now we have a fairly slow readout and cavity emptying. That is due to the design that we have. We have a relatively small chi and kappa. We also have a fairly slow initialization because we're not doing any active reset. And this is also without active reset. So for active reset, we actually need to do, you have to read out and you have to determine the state very fast. So I place this latency budget with this small kappa and small chi. We need at least 3 microseconds, usually more. And this latency budget, what I mean is that from the time you start the measurement until the cavity is emptied. So, once within this latency budget, right after this, you could run some other qubit gates. But this doesn't mean, and then I'll just discuss what's in progress and what we're working on. What we like to have is fast readout and also fast reset. So with that, using FPGA, we could do fast readout and cavity emptying. just by designing it, just by engineering, just changing the kappa and chi's. And you could also do fast initialization by doing active reset. And here, a 2 latency budget, depending on how we design the kappa and chi, we could have this latency budget to be less than 1 microsecond, or with the higher chi, we could actually reach this 500 nanosecond. And using FPGA, this latency budget actually would include the time it takes to determine the signal. So you could do an active reset right after this 500 nanosecond, and then restart a new experiment. So this is something that we're working on. And now on coherence and scaling. So throughout many years, over the years, we have, in superconducting qubits, we have made tremendous improvement in coherence time. And now we're reaching over 100 microsecond using a 10 to 100 nanosecond gate times. So it's very important to note not just the coherence time, but to understand that we need fast gates. Having 100 microsecond gate coherence, with microseconds and tens of microseconds of gate is not going to do much. And this is also an active area of research where we're studying some materials or other things to try to improve coherence. So in terms of scaling, here are different devices that we've had at IBM, starting from a 2-qubit device that I showed you earlier, 3, 4, 5. This is one of the quantum experience device, the 7, 8, and then the 16-qubit 22 buses. That's the newer quantum experience device, IBM QX5 that we have now. And we have also announced our commercial program, the 20-qubit and 50-qubit device with these connectivities. So we're always, along with improving the coherence, we're increasing the number of qubits. And what are the other things that we're working on? So quantum gates. So this, again, is going to go back to basic. How do we control the qubit state? So for single qubit, you want to bring qubit on this block sphere. And how we do it is by putting this microwave tone through this readout resonator. Our typical qubit frequencies are around 5 gigahertz. And by putting this tone, you could rotate the qubit, you could derive the oscillation, and by pulse shaping, you could prepare like an X gate or a Y gate, and you could calibrate that well. This is a picture of Jerry just in the lab in front of the equipment. Okay, so here I'm showing 2 different phases. So as I said, depending on the pulse shape that you make, you could rotate the qubit 90 degrees, and then just by changing the phase, you could do a Y90 operation. So this is the same calibration method you use, calibrate a X90 gate, and just by having an extra phase or an angle, changing the angle, you could apply a Y90 gate. So how about Z gate? Z gate is a little bit different. You could look at Dave Mackay's paper. It's a special gate where it's just done in software. So I said going from X90 to Y90 is just the change in the angle. So for phase gate, the way we implement the gate, you could do this in software, so it's kind of a virtual Z gate. So this gate for our system doesn't cost any time. So you could think of it as a free gate that you could apply. So these were single qubit gates. How about 2-qubit gates? In superconducting qubits, there are different types of 2-qubit gates that you could use. Here's some list. But for this talk, I'm going to focus on the first one, cross-resonance gate. It's a CR gate. And the pro is that you could use fixed frequency qubits, and it has fairly long coherence. But the cross-resonance gate work well within certain frequency range, so that could be difficult. Nonetheless, we have qubits, where the cross-resonance gate is an all-microwave entangling gate. So as I said, you could use this fixed frequency qubits. And 2 qubits are coupled with this static, there's a static J coupling through this bus that hybridizes the qubit levels. And so here's qubit 1, qubit 2. By driving the first qubit, the control qubit, at the frequency of the second qubit, qubit 2's tone, you could drive this ZX term so that it only drives the second qubit depending on the state of the control. So this ZX that you get from this cross-resonance gate, that is the gate that we use to make a C0 gate. So back in 2011, there was the first experimental demonstration using this cross-resonance gate. And back then, there was only, you use this single cross-resonance gate, and the fidelity of the gate was in the order of 81%. But over time, we've implemented echo sequence, and most recently have done an active cancellation with the same echoing sequence, but with active cancellation to cancel out extra terms in the Hamiltonian. So the cross-resonance gate has this ZX term, but there are other terms that we don't want when we're making a C0 gate. So with that, we have reached 99.1 gate fidelity looking at the interlead randomized benchmarking. So here, up to here, single qubit and 2 qubit. And what are the other multi-qubit characterizations that you could do? So with 2 qubit, the typical experiments that we run, because we have this always-on coupling with this bus, we typically look at ZZ coupling, the static ZZ that exists. So the type that we run, the experiment that we run, we call it the joint amplification of ZZ, the JAZZ. We run 2 different experiments. For the first qubit, this is the qubit that you're going to be measuring. You bring it to, you apply a pi over 2, and you do an echo, the pi, and then another pi over 2 in a different angle. This is not too important here, what we're doing here, but the difference is that for the first experiment, we have the second qubit in excited state, and the other experiment, you run it without this pi. And then you're going to compare the frequency difference that you observe on the first qubit. By comparing this frequency, you obtain that for this sample, for this 2 qubit, we had a 300 kilohertz static ZZ. So you could run this ZZ experiment, the JAZZ experiment, on a multi-qubit system. This is from an IBM QX1 device. It was the first IBM Q experience device that we had. And here's a table of ZZ between all the pairs. And these epsilons are just if the ZZs are fairly small, which makes sense with the D1 and D3. It's not on the same bus, so there's a negligible ZZ coupling. So as you see from this table, D1 and DS1 has the highest ZZ, just about 90 kilohertz. So when you characterize the qubits, you could get the frequencies, and then to characterize the gates, you could run randomized benchmarking. So typical experiments that we do to verify the gates are running individual randomized benchmarking. That means you run benchmarking on single qubit while all the other qubits are in the ground state. And you could also run simultaneous randomized benchmarking. That is, you run proliferate randomized benchmarking on these single qubits all at the same time. And what I want to show is comparing this row and this row, the largest change that you see in the error are on D1 and S1. So this randomized benchmarking result is capturing this ZZ, the high ZZ that I have between the pair. This is one method of looking at crosstalk on a multi-qubit system. So what are other things that we could look for? So when I ran this 422 code experiment, this looking for error wasn't the point of this experiment, but nonetheless, I was looking at the 422 code. Just to briefly go over what this is the 422 code is a 4-qubit code. There's 2 logical state that you could encode, L1 and L2. And the idea is the L1, one of those 2 logical qubit could be prepared full torrently, but the other one is not. So, for example, the logical 0,0 state, the little p, that's the protected qubit, and then the other one is a gauge qubit. So the protected qubit, this is the one that you could prepare full torrently. And these are the 2 stabilizers. And you could define all these logical a bit flip and phase flip for each of the logical states. So the experiments that I run was to first prepare a logical plus plus state. That is by running the X stabilizers and then preparing the state by measurement. So I start with the syndrome qubit at the excited state, and then at the end, I only post-select when the syndrome is at 1, and that this would prepare this plus plus state. So once you prepare by measurement, you could do a post-rotation to run state tomography, measure the rest of the 4 qubit, and make a reconstructed states. So typically for reconstructed states, you'll use the computational basis, but to look at these logical qubits, we're going to define a new basis where the first 2 strings are going to be the logical states, and then the third and the fourth are syndrome bits, which one of them detects the phase error, and the other one detects the bit flip error. So these syndrome bits could be flipped by using these destabilizers, and these change the stabilizer eigenvalues without changing logical observables. So looking here, so you could start from, say, a 0, 0 or a plus plus state, and here I'm writing a perfect 0, 0. The SZ and SX is 0, 0. So this is the proper logical plus plus state, and by applying either a phase flip or a phase flip on the logical 1 or applying destabilizer, you could change these bits, the 4-string bits. And this is going to be the new basis I'm going to use to look at the reconstructed states. And just to note that I'm going to define the acceptance probability, which means the probability that the state is in this encoded state, as probability of SZ and SX being 1. Being in 0, 0. So here's the result when you use that the C0 gate that I had from the 5-qubit device. And here, corner on the yellow corner, this is the qubits that's in the logical space. And when you actually look at the acceptance probability, it's very low. It's less than 30%. So clearly, there are a lot of states that is outside in this code space. And so from this, you could see that the code is very sensitive to certain errors. So when I was looking at these 2-qubit gate and run randomized benchmarking, each individually, these 2-qubit gates had a decent gate fidelity. So I didn't assume to get this bad of acceptance probability. So what is the type of error that we have? So I talked about cross-resonance gate a little bit earlier, and this ZX, so this is the drive Hamiltonian, the CR drive Hamiltonian, and this ZX term, this is the one that you want to make the C0 gate. And so this is the terms between this control and target qubit. And when you apply this echoed cross-resonance gate, what you're doing is you're canceling out all these terms, except for IZ in this line. But when you consider not just this 2-qubit, but other qubits that's coupled to this pair, say D2, 3, and 4, which I'll call them spectator qubits, and when you actually consider other Z terms that's associated with it, this echoed cross-resonance, two-pulse cross-resonance gate only cancel these terms out, and there are several other Z terms that's left. So how do we get rid of that? So you could do some other echoing scheme where you could divide it up to 4 cross-resonance gate and do a 4 CR pulse C0 gate. So by splitting these gates, you could cancel all these other Z errors. So here, there are 4 pairs of CR, and all the C0 gates were less than 2.5% error. And for the 4-pulse CR, the error per gate was a little higher. That's mainly due to the gate being a little bit longer and also having more pulses. Nonetheless, when you actually run the same experiment trying to make this logical state, the 422 code state, so here's the previous result using the 2-pulse CR, and this is with the 4-pulse CR. So now, as you see, most of the states are in this accepted state. It's 79% acceptance probability. And then, so you could see, and all the errors that we had previously is gone. So by running this state tomography of this 422 code, we noticed that there was some sort of error. It didn't tell us what exactly, except for that it was a bit flip, but in plus states, so it's more of a phase flip. And then we were able to come up with a different scheme of gates so that we get rid of this error. But this is not a very convenient way of figuring out that there's an error on your multi-qubit system. And the state tomography does take a long time. It's compared to methods like randomized benchmarking, which doesn't take a lot of time. It's fairly easy. So what are some other methods that we could use to understand our gates? So some of the verification toolbox that we have discuss are the randomized benchmarking. So we have the standard RB, interleaved RB. I didn't talk about purity and leakage, but these are all kind of standard randomized benchmarking that you could run on single qubit. And for multi-qubit, so you could run the standard n-qubit RB. So I've done a 2-qubit RB, but you could think about doing a 3-qubit RB. And the simultaneous 1-qubit RB, this was done on this device where we saw some ZZ errors. But also, instead of just running this 2-qubit RB and a single qubit simultaneous RB, you could run this simultaneously to see what other errors that you might to see that there is an error. So here is a picture of our IBM QX, the 5-qubit device. And so these are the typical numbers that you would get on our quantum experience website, the T1, T2s, and the single qubit error per gate, 2-qubit error per gate. And also we have this ZZ information on our spec sheet, which you could get it from our quiz kit or our GitHub. Okay, so now this 2-qubit RB, this is the number that we provide. But let's start looking at some other things like simultaneous 2-qubit with single qubit RB. On our current IBM QX4 device, so one of the pairs, C020, here's a number that you get from a 2-qubit experiment, 2-qubit RB experiment. We get about 2.4 error per gate. And when you actually include this other spectator qubit and run 2-qubit and single qubit RB, actually for this gate, it doesn't change much. And this is showing that there's not a lot of crosstalk, which is good. So let's look at another pair, CR34, so CX34. So again, the error per gate is less than 3%. But once you add this central qubit, now the error per gate is above 7%. So just by doing this simultaneous 2-qubit and 1-qubit, we clearly see that there is some sort of crosstalk, and we see this error. So now you could use, this is a fast method to see that there is some type of crosstalk, and now we could try to think about how we could correct for this. So just to kind of see, this is some new experiments that we're running. There will be a new manuscript by Dave Mackay soon on arXiv, I hope. So some 3-qubit RB could be another way of seeing some multi-qubit crosstalks. So it's just a standard 3-qubit RB, and depending on the connectivity, so you see, so usually we don't have a 3-qubit entangling gate. We would have a 2-qubit entangling gate, but if they're fully connected, to create one 3-qubit Clifford, you need about 3.5 C0s. And if it doesn't have a full connectivity, it requires more C0s. So clearly, you would be able to run it better when you have a better connectivity. So here's some results from IBM QX4. So here's the 3-qubit benchmark RB. And I'm putting down the 2-qubit RB results just by looking at the 2-qubit individually, and then by looking at 2-qubit and 1-qubit. So again, this gate doesn't change much, and none of these really made a lot of difference. And the number we get from the 3-qubit error per Clifford is sort of in the order that we would expect from this 2-qubit gate. So, but with the same pairs, but with limited connectivity, so that I took out one of the C0, now you're using a lot more C0 gates per 3-qubit Clifford. Now the 3-qubit error per Clifford is a little higher, but again, by knowing how many C0s and these errors, the error per Clifford matches fairly well to what we would expect. So here, it's probably what you might want to see, our new 20-qubit device. So here there are 20 qubits with all the couplings. It's showing the T1, T2s, and the C0 gate between the pairs that are coupled. And as you see, we have decent T1 and T2s for all the qubits. And this is very different from the type of device that we have from the quantum experience, 5-qubit and 16-qubit, mainly in terms of this is one of the first devices that we're showing where it's not, you could control some qubits that are not on the edge of the sample. So these are just the numbers that we would typically put on, the similar number as what we would put on in the quantum experience. And on this device as well, we've run a 3-qubit RB. And again, so for this one, it didn't run the simultaneous 2-qubit and 1-qubit, but using the 2-qubit RB from the mapping, the previous mapping, you get, from these numbers, it should be, the error per Clifford should be a little lower, but probably by looking at the 2-qubit and single-qubit RB, you probably could be able to see a fairly appropriate number for the 3-qubit error per Clifford. And again, same pairs, but with the different connectivity, and you see that the error per Clifford goes up. So all that together, I'd like to discuss a little bit about quantum volume. So quantum volume is something that at IBM we've been talking about, in terms of what type of metrics that we could use to describe how good our quantum processor is. So as we increase the number of qubits, more number of qubits is good. But if you don't decrease the error rate, it doesn't do much for us, right? So you want more qubits, but less error. And from the 3-qubit RB as well, you see that more connectivity that you have, you could run more things. So the more connectivity is better. And also gate set. So right now we have just a C0 gate for an entangling gate. But if you have some other gates, that would help you in terms of creating some algorithms. So to quantify this, trying to quantify this quantum volume, you could think of the number of qubits as a width and some depth d to think about this circuit over some gate set. And the total space-time volume circuit, V, is this number of qubit times the depth. And this is limited by the effective error rate, right? So what we want to come up with is a number where it actually kind of describes how good this device is. And so we want to come up with the largest square here. So we're going to define quantum volume as 2 to the minimum of either the number of qubits or depth. So we're doing this because we tried to improve the 2-qubit gate fidelity, and we'd like to do that, right? But just with 2 qubit, even if you do run more and more depth, you could easily simulate a 2-qubit system. What we want is that good low error 2-qubit error rate, and also the depth. So the model algorithm that we are going to use is, this is just a random 2-qubit gate unitary, the SU4 gate. Choose from some SU4 gate, SU4 gate. You permutate these qubits, and you choose another random 2 pairs from the set of qubits. And how we're going to define of a unit of depth is just operation of 2-qubit unitary on a pair of qubit. So we're going to assume that circuit is, we could simulate this circuit. And so we're going to have this ideal output probability, and then we're also going to have this experimental probability, output probability distribution. And you could consider 2 different metrics. One is how far away these ideal and experimental states are. It's L1. And then you could also think about probability of heavy output, which is described in this Aronson and Chen paper. I won't explain it here. So just an example, this was the data taken on our old quantum experience device, IBM QX2 device. So here's the simulation with depth 1. So that requires, so this is on 5 qubits, but for depth 1, we only requires, for this example, it required 6 CNOTs. And then this is the experimental result. And you see that, most of them are, this corresponds fairly well. But with depth 4, and this is requiring now 39 CNOTs. Now the output distribution is fairly random now. So when you plot this out, the number of qubit, you look at different number of qubits on the same device, and then you run this model algorithm many times on different depth, and you could plot out the probability of heavy output, and we kind of just could define, success as say 2/3 if you have the probability of heavy output as greater than 0.6, and if you define it this way, we get a quantum volume of 8. That is, we could, we have, 5 qubits total here, but we could only go up to depth 3. So similarly, you could run it for the 16-qubit device. And here you could run it on 3-qubit, 4-qubit, 5-qubit, and even more. But again, you don't reach any improvement in terms of depth. So for the IBM 5-qubit and 16-qubit device, even though we have the more numbers of qubit on the 16-qubit, we have equal quantum volume, which now we have it as 8. So here, when we went from 5-qubit to 16-qubit, we didn't really improve too much in terms of the gate errors. So this is shown from this quantum volume metric. So to finish up the first part of the talk, or most part of the talk, we talked about what the qubits that we have and some characterization methods. And so we're always working on improving coherence, gate fidelity, and readout as we scale up. So that's what we need. And I've defined a metric, quantum volume, to kind of start using to understand that how well we're doing, how well we're improving on all these aspects of the device. So just very, very quickly, And I think most of the people in the audience probably know the experiment well. But it's a quantum chemistry with noisy superconducting qubits. I could probably skip the motivation. And the idea is to find the minimum energy of this electronic structure problem. And that could help you to find the reaction pathways, reaction rates, and molecular geometry. So again, so the type of experiments that we want to run, we run was this hybrid quantum classical approach. Some references here. So we would map the problem, the electronic structure problem, to qubit Paulis. And I think, I'm not sure if Sergey is here now, but you could ask Sergey all about this method that we use to lessen the number of qubits required to run this later if you want. And then we prepare some trial state using a hardware efficient way. And then you do a partial state tomography to obtain the energies. And you feed it to the classical computer. And then from that, using a classical optimization, you come up with the different parameters. And you run the experiment over and over to minimize the energy. So the hardware efficient trial state preparation uses some SU2 gate, which we could use using the single qubit rotation with some phase gate. And here, this is the U entangling gate. So this could be any entangling gate that you could have in a device. So this is the hardware efficient part. For the paper, what we did was not actually use like a C0 gate, a calibrated gate, but we just turn on the CR tone. So the CR tone, as I discussed earlier, has this DX terms, and there are some other terms as well. But for this entangling part, it's okay to have some coherent. If it's a coherent operation, it's fine. So you don't want to run something you don't understand, but by applying some CR gate, you're applying some sort of entangling gate. And with 3D plus 2n variational parameters, you could make these trial states. And also this depth, that's the number of entangling gate that you apply. You could set that by depending on the amount of coherence that you have. So just quickly, for the hydrogen, I'm showing the two different place with the two different interatomic distance at equilibrium and dissociation. So depending on that distance, you would have a different Hamiltonian. And these are the terms, the Pauli terms that you want to calculate. So we have 5 Pauli terms for the hydrogen. And out of these 5, we usually would put them together and only run a few experiments, the partial state tomography. So for these 5 Pauli terms, we only had to measure 2 different states to get those numbers. For lithium hydride, we use 4 qubits, 100 Pauli terms, so it goes up quite a bit. But again, you could put them into sets of 25, and then even more for the 6 qubit beryllium hydride simulation. There are 165 Pauli terms, but you could kind of group them into 44 sets. So this sort of came up yesterday as well, but so this dotted line on this graph, this plot, is the actual energy. The black dots are the experimental results. With these density plots is from the numerical simulation using what we understand about the device. So these are some things that we know about the device. So that what brings this error is the decoherence, sampling errors, limited iteration, accuracy of the classical optimizer, and also insufficient depth. So this kink is due to not having enough depth. So all these experiments were done with depth 1. So now it's just the conclusion. So just I want to point out 3 points from our quantum chemistry paper. The one new thing was this hardware efficient qubit mapping. Again, this could ask Sergey about this. And then also this hardware efficient trial state preparation. So this is very flexible to other hardware platforms. And also we use this fast and classical optimizer that is robust to stochastic errors. And the point was that we understand, again, the energy that we got is not, at the accurate level, but it's very, we understood it by running this numerical simulation. And by understanding this experiment, there is, it's promising in the path forward with the error mitigation method. Or you could see Kristen's paper, and he's sitting somewhere on here, so you could ask him about that. And just to wrap it up, so what do we want to run this better? So we want to increase sampling. That would improve the energy estimate, and that would require some resets. So I talked about doing some fast readout, fast reset. So that's what we're working on. That is going to help us with being able to take more samples. And increased coherence, that will let you do more depth, have more depth in the circuits. And along with that, if you have more connectivity, you actually would require less depth. So that's also what we want. So at the end, we want to work towards larger quantum volume, which should improve in all aspects of our experiments. Thanks.
Thanks, Micah, for a fascinating talk. We have time for one or two quick questions.
Hi. So in the hardware efficient mapping and bidirectional approach that you're doing, I'm worried that, it looks to me like you're doing sort of a random circuit, and then because you have these gates with sort of random parameters, and then you measure something, and then you're going to try to optimize those parameters to convert to what you want. But I think that, when you do that, and you measure pretty much whatever you measure, you're going to concentrate exponentially into the average value over the Hilbert space. I think you will have to take exponential number of measurements to then find better values for the parameters. Am I wrong about that?
Sorry, this is for the
hardware efficient mapping,
right,
hardware efficient, optimization that you're doing of the parameters for chemistry.
So for this experiment, we fixed the amount of time we applied across resonance gate, which we know how much ZX we had, how much IX or other terms that we had. So we use that number with the numerical as a model and run numerical simulation. And so this parameter, the length of the CR or the angle of the CR, this also could be parameterized. So right now the n plus 2 times, 3 plus 2 times n parameters that we run over, those were just for single qubit rotations, and we didn't actually change the entangling part. But that is a parameter that we could easily add into. I don't know if that answers. No, not at all.
No, so the parameters, it's okay, it's not a big number of parameters. I'm worried that when you try to measure to then get, whatever observable to optimize whatever you're doing, in this case, getting closer to the ground state of a molecule, your observables are going to concentrate exponentially just on, like 0 or whatever. And then you're going to take an exponential number of measurements to be able to, do a gradient descent or whatever you want to do to move the parameters to a better setting. I'm not worried about the number of parameters. It's the number of measurements to get a signal.
The number of...
Maybe I can answer that. So it's not like a fully random circuit. It is like a circuit with a certain topology that has worked for this, like small, medium-sized molecules. And then I guess if you want to scale up, we're thinking of like a mixture between UCC ansatz and hardware efficient. So it is not like completely random.
It's not quite random. It's design. Okay.
Okay, other questions? Yeah.
On the final molecule, I think it's beryllium hydride, when you showed the results of the simulation of the model, there's a second curve that appears above the ground state curve. And so I was wondering, is that the classical optimizer in conjunction with the noise model finding another local minimum in the result?
Yeah.
Okay.
Oh, for this. Yeah, yes. Yeah, no, for the other one with the two different results.
It can't be about the entanglement, though, because there's an unentangled state with better energy than that. So, just saying.
Other questions or comments?
I just want to ask, you did a lot of characterization and verification, and as we heard yesterday in Shelby's talk, theorists like to come up with, as she put it, all these sexy machine learning algorithms that experimentalists don't really want to touch. And I was wondering, as your system's getting bigger and bigger, have you ever tried machine learning to perform some of those tasks, or have you ever started thinking about that?
I mean, we haven't implemented or with machine learning, but I think there's a direction that we all need to think about in terms of characterizing multi-qubit.
Last question, Nathan.
All right. So those fancy machine learning methods are pretty cool for the record. But anyways, the question I have is for the 20 qubit system that you were looking at. Did you consider changing the effective number of qubits in order to try to optimize the quantum volume? Because you don't necessarily get the best quantum volume by turning on all the qubits. So is that the way you want to go forward, or should you always just give the quantum volume for the entire chip?
Oh, that the quantum volume question. If there's a Lev or Andrew in the audience.
Andrew or Lev? Could I just maybe ask, why optimize the quantum volume?
Oh,
I mean, I know
so
that I'm not
right.
saying it's poorly motivated. I'm just saying it's clearly a what's the word I'm looking for? A proxy. So why optimize the proxy when you know for a fact that it's a proxy?
All right. So, if anyone else wants to say something, but for quantum volume, this is not the metric that we're thinking the way that we described as the only thing that we need to care about. But we want to come up with a simple metric that we could study over different types of devices that we could easily implement to kind of have to be able to compare. So, there might be other methods, and yeah.
Okay, if there are no more questions, let's thank all the speakers from the afternoon session.